So if I share my screen with everyone, a good example of a confidence interval, since we just had our inauguration, is a campaign poll. Different polls are conducted to see what proportion of voters might support a given candidate. And I pulled up a recent Iowa poll conducted by the Des Moines Register that includes what's called a margin of error. This was a poll from last fall about our recent Senate campaign between Joni Ernst and Teresa Greenfield. So Des Moines Register conducted the poll and they asked, if the general election were held today, for whom would you vote? We can see the results below. Joni Ernst received 42% support in the poll, Teresa Greenfield 45% support in the poll. If you read the small print on the way bottom there, it says the Iowa poll of 658 likely voters. That's your sample size. They polled 658 eligible voters in the state of Iowa. It'd be really great if they could ask everyone, wouldn't it? If I could ask everyone, would there be any point of having the election? Probably not, right? Because I'd ask everyone and I would know the true support for either candidate. But that's impossible. There's a reason we only have elections once every 2 years, because it's very time consuming and very expensive. It's impossible to take a census. I can't ask everyone, so let's ask some of them. Because I'm only asking some of them, there's some error. What if my sample wasn't as representative of the entire population as it could have been? There's a what is called margin of error. The margin of error in this particular poll is plus or minus 3.8 percentage points. We define margin of error as the maximum difference between the true population parameter and the sample estimate. The true support for either candidate is no more than 3.8 points away from the results of the poll. Teresa Greenfield receiving 45%, Joni Ernst receiving 42%. Does that make sense? So let's actually create a confidence interval using the results of this Senate race poll. To write a confidence interval, I take my sample result, 45%. Think of this as kind of like your p-hat. My sample proportion of the poll, my sample indicated that 45% of the people would support Teresa Greenfield for Senate. Now there's some variability. This is just a sample, it's not the entire population. So my margin of error is 3.8%. MOE, or margin of error. The actual amount, the actual proportion for the entire set of voters is no more than 3.8% away from 45%. The actual population parameter, the actual proportion of voters who support Teresa Greenfield is no more than 3.8% away than 45%. So we're going to add on 3.8% and subtract off 3.8%. 45 minus 3.8 is 41.2. It can only be a maximum of 3.8% away, so it's no less than 41.2% and no more than 48.8% for the actual proportion that support Teresa Greenfield for Senate. Doing the same thing for Joni Ernst, take our sample proportion from the poll, 42% supported this candidate. We have a margin of error of 3.8%. 42 minus 3.8 is 38.2. Plus 3.8%, 45.8. We have some level of certainty, some level of confidence that the actual proportion of all eligible voters that support Senator Ernst is between 38.2 and 45.8%. Sometimes on the news, they'll tell you the results of the poll, and they'll say that one candidate is within the margin of error of the other. Why would that be important if one candidate is within the margin of error? Obviously, you did a pretty tight race. Is it statistically probable? Is it statistically feasible that Joni Ernst might have more support than Teresa Greenfield? Is it statistically likely or probable that Ernst is actually in the lead?
Yes.
Yes. Why yes? I would agree with yes. It's possible. It's possible.
Because she
What
could
if, Go ahead, Isaac, please.
because she could have 3.8% more than it says, and Greenfield could have 3.8% less than what it says.
Absolutely.
And then
What if
more?
Yeah. What if Greenfield has some value less and Ernst has some value more? Because they're within the margin of error, I have a difference of 3% with a margin of error of 3.8%. It's actually feasible that Ernst could be in the lead. Within the margin of error. It's a close race. Based off of our poll, I can't really say who's in the lead or not because they're within the margin of error. It might actually be that Ernst has more support than Greenfield based off of my poll results and margin of error. All right, so I have about a short 10-minute video that explains in a little bit more detail about confidence intervals, distributions, and sampling. So let me get that going for you. Then we'll come back and talk more about creating and interpreting confidence interval for sample data.
In an election season, if there's a runoff between candidate A versus candidate B, we are pollsters. We're interested in figuring out what's the likelihood that candidate A wins this election. Well, ideally, we would go to the entire population of likely voters, 100,000 likely voters. We would ask every one of them, who do you support? And from that, we would be able to get the population proportion, which would be, this is the proportion that support candidate A. But it might not be realistic. In fact, it definitely will not be realistic to ask all 100,000 people. So instead, we do the thing that we tend to do with statistics is that we sample this population and we calculate a statistic from that sample in order to estimate this parameter. So let's say we take a sample parameter. So this is sample size, say n equals 100. And we calculate the sample proportion that support candidate. So out of the 100, let's say that 54 say that they're going to support candidate A. So the sample proportion here is 0.54. And just to appreciate that we're not always going to get 0.54. There could have been a situation where we sampled a different 100 and
different sample,
we would have
different
maybe
results.
gotten a different sample.
It's called sampling variability.
That one we got 0.5.
Variability in our sample.
And we already have the tools in statistics to think about the distribution of the possible sample proportions we could get. We've talked about it when we thought about sampling distributions. So you could have the sampling distribution of the sample proportions And it's going to, this distribution is going to be specific to what our sample size is. For n is equal to 100. And so we can describe the possible sample proportions we can get and their likelihoods with this sampling distribution. Look at something like this. Because our sample size is so much smaller than the population, it's way less than 2%, we can assume that each person we're asking that it's approximately dependent. Also, if we make the assumption that the true proportion isn't too close to 0 or not too close to 1, then we can say that, look, the sampling distribution is roughly going to be.
What theorem guarantees that?
bell shape. But we know a lot about the
Sampling distributions are normal.
We know already, for example,
Given some
this is
reasonable
what
assumptions
you're
made.
watch the videos on this, that the mean of this sampling distribution is going to be the actual population. And we also know what the standard deviation is. So it's one standard deviation, it's two standard deviations, it's three standard deviations. Above the mean, that's one standard deviation, two standard deviations, three standard deviations below the mean. So this distance is this standard deviation right here, which we denote as the standard deviation of sample proportions, or this is sampling distribution. This is, we've already seen the formula. It's the square root of P times 1 minus P.
We use P times Q. 1 minus Q is the same thing as Q.
Divided by our sample size. That's why it's
The standard deviation of sample proportions is the square root of P times Q over
so in this first scenario, let's just focus on this one. Right? When we took a sample size of n equals 100, we got the sample proportion of 0.54. We could have gotten all sorts of outcomes here. Maybe 0.54 is right over here. Maybe 0.54 is right over here. And the reason why I have this uncertainty is we actually don't know what the real population is. What the real population is. Let me ask you maybe a slightly easier question. What is the probability that our sample proportion of 0.54 is within 2 times 2 standard deviations of P? Pause the video and think about that.
what proportion is within 2 standard deviations given a normal model?
Calculate the sample proportion rate.
95%. We are 95% certain
That's essentially
that P hat is within 2 standard deviations of P.
And we know from studying normal curves that
Sample proportion is within 2
95%
standard deviations of P 95% of the time.
This is approximately 95% of the time that I take a sample size of 100 and I calculate this sample proportion. 95% of the time I'm going to be within 2 standard deviations. But if you take this statement, you can actually construct another statement that starts to feel a little bit more, as we could say, inferential. We could say there is a 95% probability that the population portion P is within 2 standard deviations of P hat, which is equal to 0. Pause this video.
That's really important because we're going to use P hat to estimate
There's a
P using the sample
chance
estimate
that our
population.
sample proportion
95% chance that it's within 2 standard deviations of each other.
Well, that's equivalent to saying that there's a 95% chance that our true proportion is within 2 standard deviations of our sample proportion. And this is really, really interesting because if we were to be able to figure out what this value is, well, then we would be able to create what we could call a confidence interval. Now, you immediately might be seeing a problem here. In order to calculate this, our standard deviation of this distribution, we have to know our population parameter. So pause this video and think about what we would do instead. If we don't know what P is here, we don't know our population proportion, do we have something that we could use as an estimate or a population proportion? Well, yes, we calculated P hat already. We calculated our sample proportion. And so a new statistic that we could define is the standard error. The standard error of our sample proportions. We can define that as being equal to, since we don't know the population proportion, we're going to use a sample proportion. P hat times 1 minus P hat, all of that.
Standard error is an estimate of the standard deviation using the sample statistics instead of the population parameter. Using P hat instead
This
of Q.
actually is an unbiased
Q hat instead of Q.
for this right here. This is going to be equal to 0.54 times 1 minus 0.54, so 0.46. All of that over 100. So we have the square root of 0.54 times 0.46 divided by 100. Close my parentheses. Enter. So if I round to the nearest hundredth, it's going to be actually around to the nearest thousand. It's going to be approximately 5 hundredths. So this is going to be approximately 0.05. So another way to say all of these things is the
These standard errors you have to add on
but
to
now
be
we
within
have
95%.
So we can now say with
95% of the distribution is within how much?
95% confidence.
Two
That
standard
will often
deviations.
be known as our
Or since we're using
confidence
sampling data,
here.
2 standard errors.
95% confidence between, and so we want to go 2 standard errors below our sample proportion that we just happened to calculate. So that would be 0.54 minus 2 times 5 hundredths. So that would be 0.54 minus 10 hundredths, which would be 0.44. And we'd also want to go 2 standard errors above the sample proportion. So that would be that plus 10 hundredths. And
We did that with Greenfield terms. We added on what's called the margin of error. So we're relatively confident we've captured the true population proportion, true amount of support for either candidate.
And so this interval that we have from 0.44 to 0.64, this will be known as our confidence interval. And this will change not just in the starting point and the end, but it will change the actual length of our confidence interval. It will change depending on what sample proportion we happen to pick for that sample. A related idea to the confidence interval is this notion of margin of error. Margin of error. And for this particular case, for this particular sample, our margin of error, because we care about 95% confidence, so that would be 2 standard errors. So our margin of error here is 2 times our standard error, which is B 0. And so we're going 1 margin of error above our sample proportion, right over here, and 1 margin of error below our sample proportion, right over here, to define our confidence. And as I mentioned, this margin of error is not going to be fixed every time we take a sample. Depending on what our sample proportion is, it's going to affect our margin of error because that is calculated essentially with the standard error. Another interpretation of this is that the method that we used to get this interval, the method that we used to get this confidence interval, when we use it over and over, it will produce intervals. And the intervals won't always be the same. It's going to be dependent on our sample proportion. But it will produce intervals which include the true proportion, which we might not know and often don't know. It will include the true proportion, 95%. I'll cover that intuition more in future videos. We'll see how the interval changes, how the margin of error changes. But when you do this calculation over and over and over again, 95% of the time, your true proportion is going to be contained in whatever interval you happen to be. Now, another interesting question is, well, what if you wanted to tighten up the intervals? How would you do that? Well, if you wanted to lower your margin of error, the best way to lower the margin of error is if you increase this denominator right here. And increasing that denominator means increasing the steps.
By dividing by a larger number, I decrease the standard error. I decrease the length of the standard deviation, and thereby shrink the margin of error.
But I'll leave you there, and I'll see you.
Get off that for a minute. Some information here on margin of error and standard of error, and how we construct confidence intervals based off of margin of error. Kind of putting a pin in, well, putting a bow on some of the material discussed in that video. Margin of error is the maximum expected difference between the parameter we're estimating using our sample. I can differ, for example, from our poll, no more than 3.8% for my estimate for either candidate. So we add on the margin of error to get the right endpoint of the confidence interval. We subtract the margin of error to get the left endpoint of the confidence interval. The standard error is an estimate of the standard deviation of the sampling distribution using our statistics. The standard deviation of p hat is the square root of p times q over n. It's from our last standard sampling distributions. And I'm trying to estimate the population parameters, population parameter p and q. I don't know those yet. So the best we can do is an estimate of those values using the sample statistics. That is what's called the standard error. Standard error. The square root of p hat times q hat. These two are identical. I'm just replacing parameters for statistics. Population values with sample values, right? P and p hat should be relatively close to each other because my sample should reflect the overall population. This is the best we can do using sample data if we're trying to estimate the population values. Same thing with x bar. The standard deviation of x bar is sigma over square root of n. Sigma is a population standard deviation. I don't know that because I'm just taking a sample from my population. I don't know the entire population values. So the standard error of x bar places sigma, the population standard deviation, with s, the sample standard deviation. We use those as an estimator of the standard deviation of our sampling distribution. Let's come over here and look at our normal model. By central limit theorem, our sampling distribution should be normal, following a few different reasonable assumptions we talked about. So I take a sample, and I call it p hat. I want to create an interval, called a confidence interval, where I'm relatively certain that the true population parameter would be contained. So using a normal model, I can see how many standard deviations I need to add and subtract so that I'm contained a certain amount of the distribution. Within 95% would be how many standard deviations? 95% would be how many standard deviations? 2. Within 3 standard deviations would be 9.7. Within 1 standard deviation would be 68%. We use z-scores. Z star is a critical z-score that we need to use to capture a certain part of the distribution. How many standard deviations do I have to add on so I've got 90% of the distribution contained, 95% of the distribution contained, or so on? I want to be more likely, I need to have a larger z-score so I've captured more of the distribution. I want it to be more likely I've captured the true population parameter, I need to have a larger z-score so I've captured more of the distribution. That margin of error is our z-score that we know by saying, all right, how likely do I want it to be I've captured the population parameter times our standard error. Standard error is an estimate of the standard deviation of our sampling distribution. How many standard deviations do you want to add and subtract so that you have some degree of certainty you've captured the population proportion? That's what margin of error is. How many standard deviations do you want to add or subtract off of your estimate so that you are relatively certain you capture the population? I want to be more confident, I have to add on more margin of error so I go further into the details. If I don't need to be quite as confident, I don't have to go quite as far out, so my z-score, how many standard deviations I have to add on, will be smaller. That make sense? We'll talk more about our critical values of z. I call this z star, our critical z-score value, tomorrow. Once I add and subtract the margin of error, I have what's called the confidence interval. P hat plus or minus the margin of error is our confidence interval, where I have some degree of certainty that the true population value, the true population parameter, would be contained within. Questions you have there? let's, with the time we've got here, look at interpreting confidence intervals. Since confidence intervals are inference in context of some population, how we interpret them is somewhat important. So if I pull up this confidence interval GeoGebra link, not that one. There you go. Let's look at this. This is going to construct a confidence interval to estimate some population parameter. I'm going to do a confidence interval that hopefully contains my population value of 0.5. I'm going to take a sample. I'm going to use that sample to create a confidence interval. Hopefully that confidence interval contains the true population proportion. So let's sample. This green bar shows up representing the confidence interval. It's green because does this green bar overlap with my p-value of 0.5, my population parameter? Does it overlap? Does this interval contain the 0.5 value? Yeah. It's green because it contains that population parameter. Within my confidence interval was the true population proportion. I could sample a bunch of times. Oh, now I find a red one. Is my population parameter within the confidence interval? No, it was not. It's too far to the right. My sample proportion, p hat, was too far to the right, too much above my 0.5 population parameter. So when I added and subtracted my margin of error, it didn't overlap. It didn't overlap with my parameter of 0.5. That's going to happen because we are 95% confident that each of these different confidence intervals contains the true population parameter. If I run this applet and construct 100 different confidence intervals, how many of them, there's some variability, but how many of them should contain, how many of them should overlap with 0.5? Second, Chris? 95. Because we're 95% confident, right? So if I increase my intervals from 1 at a time to 100 at a time, there's our 100 different confidence intervals that we made by sampling from this population 100 different times. How many of them hit? How many of them missed? Ooh, I had a little bit, I didn't do quite as good as I was supposed to. I only had 92 because there was some variability. 92 of them contained my 0.5 value, my population parameter. Supposed to be about 95, but because of some variability and some randomness, I just got a little bit less. See if I can do this a little bit more here. Now I had how many of them not contain 0.5? How many of them did not contain the population parameter? 4. 96 hit that, overlap with that value. The 4 in red didn't. What if I adjust my confidence level to 99%? What's going to happen now? If I draw a sample of 100 different intervals, how many of them should contain 0.5 overlap with it? 99 of them. So sample. 2 of them did. 98 were hits, 2 of them were misses. That level of confidence tells us how likely we are that we've captured the true population parameter with our interval, with our confidence interval. All right, so would you grab your own laptops and let's pull up some practice. I want to walk through a couple of different examples that are on the S19 practice document that get us a good start on interpreting confidence intervals. Every single time we conduct inference, we have to interpret our results. Every single time we conduct statistical inference, we have to interpret our results. So interpretations is very important. It's not enough to just get the answer. You have to tell what it means. So on the board behind me here, we're going to walk through the first 3 off of this S19 practice document. Isaac, Connor, you guys doing okay?
Yeah.
Yeah.
Awesome. We're just going to run through a couple of these here if you want to follow along on that practice document, and we'll show the work up on the board here.
All right.
All right. So after we've had some information today, let's answer a few of these questions. A TV newscaster reports the results of a poll and says the margin of error is plus or minus 4%. What does that mean? So we're off by no more than 4%. The poll results are no more than 4% away from the actual support for the candidate. The results of the poll are no more than 4% away from the true proportions. The entire population of voters. Margin of error is the maximum difference between our sample estimate and the population parameter. From there we go. No more than 4% away from the true proportions for the entire population of voters. Whatever the poll is telling us, it's no more than 4% away from the actual proportion from the poll result. Number 2. What fraction of cars are made in Japan? The computer output given below summarizes the results of a random sample of 50 different cars. Explain what it tells you. When I interpret a confidence interval, let's first say what degree of confidence, what's our confidence level in the interval? What level of confidence did this generate? 90%. We are 90% confident that the actual proportion of cars what? Made in Japan. Between what 2 values? Between what? 2994, if you went around there. And what? 469. By looking at 50 different cars and recording the proportion of those cars that were made in Japan, I was able to estimate the actual proportion of all the cars out there that are made in Japan. We're 90% certain that it's somewhere between 29.9% and 47%. Would you guys try your hand at running the interpretation for number 3? Number 3, call it a day. A study of 902 decisions made by the Nebraska Board of Parole produced the following computer output. Assuming these cases are representative of all cases that may come before the given board, what can you conclude? What does being paroled mean? Just for some context here. You're paroled. Everybody know what that means? Let out of jail. You're done serving your time. You're paroled on good behavior or something, maybe, right? Sure. You might have some conditions on your parole, but you're no longer required to stay in prison. Might be under house arrest or have to meet with the probation officer or whatnot. Write the interpretation for the confidence interval shown. You should start my level of confidence. Go from there. How'd you guys do this? With 95% confidence? Portion of cases paroled. How about all cases? There we go. It's referring to a parameter value, population score. Finish the rest up. Somebody else. Proportion of all cases paroled in Nebraska. Between, what were those numbers there, Nora? You said,
561.
yeah, 561 and 6252. Between 56 and 62.5% of all cases before the board should be paroled with 95% certainty. Right, call that good. We'll look at some more critical Z scores tomorrow and begin writing our own confidence intervals.